Okay, I think it should be working, but anyway, so okay, good. Um, so testing. Okay. Hello, long time no see. Yeah. So even this live is mainly about the study of this textbook. If you have any math questions, you can always bring up, and we can try to figure out how to solve it. Okay. Otherwise, I'll just continue showing what this is going to be. So this is going to be sort of like a chapter zero or episode zero here. Uh, this is just testing. Well, yeah, first live stream here. So let's see if any side was good, and then after that, we probably try to do every day at some point. Currently, I'm not in the US, so the time will be a little bit different. So the starting time of the stream will be a little bit vary, but anyway, we'll try to keep it up. So for now, today the main goal is trying to type in most of the problems from the textbook that we're going to go over, and then starting from the next one, we're trying to do probably 2 hours for a stream, and either we'll spend 2 hours on one chapter, or if we try to finish one chapter in one stream, but maximum 2 hours. If we couldn't finish it, we'll just continue on the next day. Okay. Um, so yeah, where am I? That's a good question. Right now, I'm actually back to Hong Kong, just to do some personal stuff. But at the same time, I'll have a little bit more time to do back to YouTube and try to bring some math problems up. But of course, since I'm actually out of country, I don't have the whiteboard with me, so it'll be hard to actually make problems or videos with problems on the whiteboard. So instead, I decided to try to pick a textbook that I've used back then when I was in college. And try to go over answers. And these textbooks are can say as for math majors, but of course we can also try to pick something for non-math majors, something a little bit easier like calculus or maybe even pre-calculus, for instance. So as you can see from the screen, uh, there are actually 46 chapters. Currently, I'm actually at chapter 30. Let's see, it should be down here, chapter 30 somewhere. Yeah, it's actually down below. Let me see how to get there. I think it's somewhere around here. Nope, that's chapter 19. Here. Okay. Yeah, it's somewhere down below. Anyway, yeah, chapter 27, chapter 28. I'm still typing up copying the problems so that later on you guys will actually see the problems easily when I'm trying to answer it or when we're trying to go over the answers. Okay, yeah, as you can see, chapter 30 is not done yet. We'll try to see how far we can get. And also, In fact, chapter one has already gone through. So this textbook is actually called A Friendly Introduction to Number Theory, uh, written by the author, Joseph Silverman. And of course, you can try to look it up online and see how where you can buy it. And for now, I'll only type the problems here on this file, as well as going through the answers by typing up the answers. So you can actually see that um, we will have the problems and then the solutions right down below. And also, we can see that for now, I've actually finished chapter one already, but we can also go over the answers in chapter one in today's stream. So again, what's number theory? Well, number theory is just a study of numbers, in particular, a study of integers, or uh, more narrowly saying, we will study the positive integers, aka the natural numbers. Well, if we don't include zero as natural part of natural numbers, and I personally don't include it, just like how this textbook does, which some people do. But when I say including zero, I give a different name, which well, sometimes some people actually will take the two names differently. I call it with zero. I call the system as the whole number. Okay, some people might say the whole number is the positive integers, and uh, with zero, including zero, it will be natural numbers. But I'll take it the other way around. Anyway, this is the term that we're going to use, just to clarify. So, Why do you want to study number theory? Once again, we would like to study integers, especially positive integers, and try to see some special patterns that we can actually find out based on uh, how some certain setups, and such as the study of the prime numbers, as well as trying to go through the divisibility, which is actually a very fun topic, and also is very easy to understand. I remember the first time I studied divisibility was the trick of divisibility, precisely, was when I was in elementary school or primary school in the place I live. Um, and the reason that I actually studied it was because we're joining the math content. We're trying to get into competitions, and then for elementary school students, of course, the problems won't be too difficult, but then sometimes it'll be tricky. And most of the problems that they give out were like something that is asking if the number is if it's possible to be part of the answer, or something like that. And most of the time, they will just give out positive integers, and that is the reason why we would like to study like something like the divisibility of positive integers, so that we'll be able to quickly determine whether the given option is an answer or not. Now, of course, there are more to study in number theory. What I was talking about was just the introduction of number theory, which is actually part of the basically the course that I took when I was using this book. Um, so here are some of the fun problems that we can see. In chapter one, we actually get six problems. Let me see. Yeah, six problems in total. And then this is just it's just kind of like an abstract of what this book is going to talk about, and what is the meaning of number theory and what we're studying. Okay, and we're trying to give out some basic problems that, of course, what does that mean by square numbers? Meaning that 9 is a square number because 9 can be, but most of the time we're talking about positive numbers in this case. Um, that can be formed like a triangle, meaning that it can be written as 1 plus 2 plus 3 plus all the way up to some certain positive integer k. Okay, so for example, 3 is a triangular number because we can rewrite 3 as 1 plus 2. 6 is another one because we can write as 1 plus 2 plus 3. Now, 9 is not a triangular number because we cannot write as 1 plus 2 plus 3 plus up to some positive integers consecutively. And geometrically, we won't be able to make it like a triangle shape. Uh, so these are triangle numbers or triangular numbers. Then the question is asking, find the next one, and if possible, the one after that. And then can you figure out an efficient ways to find triangular square numbers? Meaning that it's a positive integer that is both a square and also a triangular number. And it is asking, do you think there are infinitely many? So in fact, if we want to find the next one is already over 1,000. Where we see it in the solution. And then the one after next is 41,616, which is obviously growing faster and faster. And for the last part of the problem, do you think there are? And that's there are infinitely many. Well, notice that we don't want to write in this n here or this kind of number, the triangular square number, uh, into two forms, right? S square and t and the triangular number t times t plus 1 all over 2. We will be able to generate this n as long as we'll be able to find some positive integers s and t respectively, so that we can put these two expressions together. So how are we gonna finish it up? So what we can do is we will have this. So notice that such n can be written as this, as long as we can find s, t. Of course, there are positive integers in this case. Oops, in positive integers, such that s squared is equal to the triangular number t times t plus 1 divided by 2. Oops. Then we'll be able to guess the answer. Okay, have a good night, Gerard. Good to see you again. So we actually get this following here. We will get a triangular square number. Okay, so we have our answer finished. Then we have a second problem here. Try adding up the first few odd numbers and see if their numbers you get satisfy some sort of pattern. Once you find the pattern, express it as a formula. Give a geometric verification that your formula is correct. So when we do that, we actually see, well, of course, if we just start with 1, 1 is just equal to 1, so we skip that. Now we're gonna take a few more, such as 1 plus 3. And 3 is the next odd number after 1. And we set it is equal to 4. If we add a 5, we will get a 9. Add a 7, we get 16. And if we keep going, we actually get the expression, implying that if we add up to some odd numbers to n minus 1, we actually get the expression n squared. And geometrically, it's true because we can actually imagine that when we take the string of 2n minus 1 block, um, you can break it into n unit L long L shape block, and then and, uh, and then we'll be able to uh, attach it to the original square shape that we have with the side length n minus 1. So what does that mean? Let's say if we have something like this, uh, two L shapes here, we'll be able to rotate it like this, break half of it and rotate it like into an L shape, and then attach it to the square that we already have, and then we'll be able to create a new square with 1 unit longer on each side. And that's how we will be able to create another square. Okay. So, yeah. I think I will be able to. And by the way, if anyone cannot see the part that I'm sharing, please let me know. Okay. Yeah, and then we have problem 3. The consecutive odd numbers are all primes, but then it's asking if there are any, if there are infinitely many such prime triplets, meaning that we have 3 consecutive odd numbers being prime. Okay, yeah, explicitly we will have prime number p such that p plus 2 and p plus 4 are also prime. So quick answer, no, there isn't any other than the example that we see, 3, 5, and 7. Now, how can we prove it? Well, we can just assume that such p is a prime. Then we can see, and of course, in this case, we will assume that p is strictly greater than 3. That means that p is not divisible by 3. In other words, if p is going to be divided by 3, it will have a remainder of 1 or 2. Or 2 we can rewrite as negative 1. But anyway, this is the symbol that we have. P is going to be congruent to plus or minus 1 and not 3. Then let me try to zoom in a little bit. Make it a little bit larger. Okay, good. It's easier to see. Maybe a little bit more. Great. Then we will actually see that either p plus 2 is going to be congruent to 0, or p plus 1 is going to be congruent to 0. What does that mean? Well, if p is going to be congruent to positive 1 and not 3, in other words, if the remainder of p after divided by 3 is equal to 1, then if we add 2 there, then p plus 2 here, after divided by 3, will actually have no remainder. The remainder is going to be equal to 0. Now, if we have the second case where p is going to be congruent to negative 1, in other words, if p has negative 1 as a remainder, which is the same as 2, by the way, we're supposed to actually have positive, no negative value for our remainders, but just for our convenience, we're going to keep it as negative here. Then what we're going to get is, of course, if the remainder is negative 1, if we add 1 to such p-value here, or add 4 to this p-value here, we'll actually get the remainder going to be equal to 0. Okay, meaning that we'll in either case we'll actually have at least one of the next two consecutive odd being a multiple of 3, which is not a prime number because we know that those two numbers are strictly greater than 3. meaning that it has a factor of 3 and some other positive integers than 1. And we will say that this number is a composite number, not an not a prime number. So that's how we actually prove this problem or prove our conclusion. Number 4, we have it is generally believed that infinitely many primes have the form of n squared plus 1, although no one knows for sure. Again, this one is is not certain yet, but we believe that it is true only because we couldn't we for now we couldn't find any we couldn't really find a general reason to counter it. Now, the questions that we have: A, do you think there are infinitely many primes of the form n squared minus 1? Well, if we have already studied basic algebra, like algebra, high school algebra, we should actually figure out that there can only be one prime of such form, which is equal to 3. And this is because we always can factor n squared minus 1 into the product n minus 1 times n plus 1. And again, we're using the difference of squares formula to get this factorization. And of course, in order to satisfy being a prime, we need one of the factors to be 1. And of course, we're assuming that both of them are positive in this case, or both of them are negative. But in this case, it will just end up with the same result. So anyway, in this case, we will need the smaller factor, n minus 1, to be equal to 1. But in this case, if n minus 1 is equal to 1, n is going to be equal to 2, and n plus 1 is going to be equal to 3. So that if we try to multiply back in, the only possible prime is 3, which is in this form. Second part B. Do you think there are infinitely many primes of the form n squared minus 2? Quick answer, yes. It is actually kind of hard to imagine right now because we cannot really do factorization of n squared minus 2 with integer coefficients like what we did in part A. But we actually will be able to see it that this is going to be true, which is actually in later on chapter. To be more precise, it will be in around chapter 20. I believe it was in. It's going to be in chapter 24 to 26, when we're going to study quadratic residue. We'll be able to learn that there are infinitely many prime numbers p, such that p plus 2 is a square. Uh, or not p plus 2. Well, yes, technically p plus 2, which is equivalently saying that p is of the form n squared minus 2. And once again, that is just basically saying that if we have n squared minus 2 is a prime number p, then if we add 2 on both sides, we get n squared is going to be equal to p plus 2. In other words, p plus 2 must be a square. Now, again, the actual understanding or the studying is going to be in like 20 chapters later. We're not going to go through the detailed parts for now. So we're going to get this answer right away first. How about of the form n squared minus 3, n squared minus 4? Well, we know that there are infinitely many primes take the form n squared minus 3 with a similar argument of to n squared minus 2. Okay, once again, we actually need to use the quadratic residue to see that coming. However, we also notice that n squared minus 4 is factorable into n squared n minus 2 times n plus 2. And once again, if this product is going to be a prime, one of the factors must be equal to positive 1 or negative 1. And of course, we are assuming that n squared minus 4 is positive. So, and then once again, that's based on the general problem here. We're assuming the primes when we are saying that, at least in our textbook here, we're assuming that we're talking about or we're dealing with positive integers. So since n squared minus 4 is positive, we are assuming that both factors must be positive or both factors must be negative. But either way, we will see that by symmetry, we can assume that both are positive and will actually end up with the same result. So because of that, we if we assume both are positive, we actually will need to assume that uh, the smaller factor, or in this case n minus 2, must be equal to 1 in order to make the whole product to be prime. And that's also giving us the answer that there can only be one such prime of the form n squared minus 4. And there will not be infinitely many primes of such form. Now, finally, in part D, we have which values of A do you think give infinitely many primes of the form n squared minus A? Well, based on the observation or the answers that we have from first three parts, we can clearly see that if A is a square, we won't be able to get any prime numbers except one of the prime numbers. And that's once again because if A is a square, we will be able to factor out uh, the form n squared minus A into n minus the square root A times n plus the square root of A. And once again, that's saying that if A is a square, meaning that we can rewrite A as something like B squared, then we will be able to get the factorization. And once we can factor out into two factors, in order to be a prime, there can only be one way, which again is uh, to set the smaller factor to be equal to 1. But that means that there can only be one way to actually get a prime number of the form n squared minus b squared. So, in order to get infinitely many primes, we need to have A to be a non-square number, such as 2, 3, not 4, because 4 is 2 squared, 5, 6, 7, 8, 9 is not going to work because once again 9 is 3 squared, 10, numbers like that, numbers that are not square. And then once again, how does it really work? We're actually going to discuss this again in later on chapters about quadratic residues. Once again, that is actually related to quadratic residues in order to help us getting the results in a more efficient way. Now, problem 5, the following two lines indicate another way to derive the formula for the sum of the first n integers by rearranging the terms in the sum. Fill in the details. So once again, how do we actually get this? Well, this is actually a method that uh, Gauss has actually thought when he was a kid, asked by his teacher, and well, kind of like elementary school back then in centuries, about how we can add up from 1 all the way to 100, and then he actually got the answer quickly, while other of his classmates were still trying to add a number by another number. And when his teacher asked him how he could get this result quickly, this is the method that he used. He took the first term and then added with the last term, and then took the second term with the second of the last term, and then so on and so forth, until later on he finished a pairing. Then for each pair, he would just add together to actually get the same results, n plus 1 or 1 plus n here. Okay, and then we'll be able to just count how many pairs of n plus 1 or 1 plus n in this case uh, we get, and then just multiply with that many copies, and we'll be able to get the result. So the question is asking how many copies of n plus 1 are there in the second line, which is this line here. So how many do we have? You may to consider the case of odd cases of odd and even n separately. If that's not clear, first try writing it out explicitly for n equals 6 and n equals 7. So we can just think of the cases. If we have n equals 6, we actually get exactly 3 pairs. 1 plus 6, 2 plus 7, 2 plus 5, 3 plus 4. In this case, it will be 3 sets of the 1 plus n situation. And if n is equal to 7, however, we actually get 3 pairs, but then we actually get an extra term, which is the term in the very middle of the entire expression. So what we can see is that if we have n is even, we actually get exactly n over 2 or 1/2 of the n copies of the set n plus 1 or 1 plus n. Now, if we have odd, of course, if we divide by 2 or multiply by 1/2, we actually get the 0.5 part here. But then that part is actually saying the number in the very middle that's being isolated and couldn't pair up. So we will still actually have a little bit less than n, a little bit less than n over 2. So in this case, we actually see that we have the number of copies that actually will be the round down of n over 2. So for example, if n is equal to 9, then we will actually have 9 over 2, which is 4.5. But if we round down to the integer, we will actually have 4 copies only of n plus 1 in the second line. And that is the solution of this problem. Last but not least, we have for each of the following statements, fill in the blank with an easy to check criterion. So part A, we have m is a triangular number if and only if something is an odd square. And of course, this expression is supposed to be in terms of m. Okay. And quick answer, we will need 8m plus 1 to be the odd square. Now, part B, we have n is an odd square if and only if something is a triangular number. And of course, our expression should be in terms of n here. And our quick answer is n minus 1 all over 8. Well, we can actually see that these two expressions are very similar to each other. In fact, if we have already studied algebra, we can actually see that these two expressions are kind of like an inverse expression or inverse relation to each other. In other words, if we think these two as functions, then they are inverse functions to each other. So that if we substitute one to another, we actually will get the m back or n back. Okay, and this is actually part C here. Prove that your criteria in part A and part B are correct. So let's start off with A here, which is taking m as a triangular number, and we want to see that's the 8m plus 1 is r squared. So how do we do it? So let m be equal to 1/2 times m lowercase m times m plus 1 here, be a triangular number. And once again, that is the expression of triangular number. Okay. And again, that is actually followed from previous problem and also problem 1 there. For some positive, some integer, let's keep it more general. For any integer n, okay, including positive, negative, and 0, then this implies that m with this expression will be equivalent to have 2 copies of m, capital M. 2m is going to be equal to we multiply it. We have lowercase m squared plus m. And then after that, we multiply both sides by 4, and after that, we just add 1 on both sides, such that on the right-hand side, we actually will end up with 4m squared plus 4m plus 1. And this, we can actually factor out as a perfect square, the square of 2m plus 1. And clearly, this is an odd square because we know that m, lowercase m, is an integer, such that 2m here is going to be uh, 2 times any integer, and it must be even by definition. And then if we have 2m being even, and if we add 1 to it, it's going to be odd. And that's how we get the odd square. Then to do it the other way around, which is actually related to the other in the other direction, we're gonna start with n. Now we assume that n is a perfect square. Now we want to see that the expression is gonna give us a triangular number. Then what we do is we set it equal to 2n plus 1 quantity squared, and of course we multiply out, and then we subtract 1 on both sides to get capital N minus 1 is going to be equal to 4n squared, 4n squared plus 4n, and of course we can factor out the 4n to get 4n times the quantity n plus 1 here, such that from 4 to 1 half, we're going to divide both sides by 8, so that the right-hand side is going to be the expression of a triangular number. So we see that this expression is going to be a triangular number for n capital N minus 1 over 8. Okay, and that's how we prove the criteria in part A and part B are correct. So that's it for chapter 1. Now we still have so today we're gonna keep it under an hour, so we still have about 20 minutes to go. So for the rest of the time, I'm gonna continue typing up the problems from from future chapters, and then of course if anyone has any math questions, you can try to ask, and we're trying to figure out how to do it. Okay. Or if you have any questions, or you can always try to type up and ask and see what we can see if I will be able to answer it. So now we're gonna move on to typing up the problems. Mm, shit. This recommendation of the Markov equation for zero. Oh, okay. 说的是 okay. The assumption is hold on like this. Versus to take for the formula. ZL. Oh, one, 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 one. These are ones. There's a delay. Okay. So now chapter 30 is done. By the way, this textbook actually has 46 chapters in total. At least it's a textbook version, and then I also heard that there are a few more chapters. They are actually online. Like when you try to purchase a book, they will give you kind of like a code, and then you can try to look up the rest of the chapters, the rest of the books, including the exercise problems for the extra parts. So now we'll just do up to chapter 46, which are actually on the textbook. I think. Um, Hopefully, yeah, this textbook will be done by like in within the, 60 days. I hope, but we'll never know. It depends how hard the problems are, and also how many problems are in each chapter. Well, I remember one of the chapters has 18 problems, and that's gonna take quite a long time to actually finish up. And also, uh, the goal of having this live stream is not only to trying to show how number theory works. Of course, you guys can actually see how these problems are done. Um, and honestly, the introduction of number theory is not as difficult as most people think. Also, if any of you have any math problems, you're always welcome to ask and see if we will be able to try to solve it during the stream. Okay, let's get back to it. So, chapter 31, we have once again the square, triangle, and numbers revisits. In other words, we're now back to what we just had in this at the beginning of this stream, chapter 1. But this time, these problems are going to be revisits, and it's going to be recreated, and also try to extend it to some other kinds of problems. This chapter, in fact, has 4 problems. Of course, it doesn't sound a lot, but of course, each problem has sub-problems or subparts. So let's see how difficult these problems are going to be. 9, 6, 10. Mm. This is not correct. Why? Mm. Forgot the period. Okay, this is not what I'm thinking of, but it's gonna be like this. Is it going to make sense like this? No, it doesn't make sense. Okay, so it's already five. Well, it's been 1 hour since the beginning. So thank you everyone for watching. Hopefully, we'll be able to continue tomorrow. And starting from tomorrow, we're gonna start actually doing the problems. So hopefully, we'll be able to finish it within 2 hours per chapter. And again, starting from tomorrow, uh, every live stream we're gonna keep it under 2 hours. So either we finish the entire chapter within 2 hours, and then we're gonna see what we can do after that, or maybe solve problems from any of you guys, or we will just try to end it in 2 hours and then continue working on the same chapter until we finish. Okay. Once again, thank you everyone for watching. I'll see you in the next stream.